Yes, any questions before we go to this example? You see, if you just follow the steps, basically what we did was we first looked at some asymptotic solutions, asymptotic behavior of the state, and we determined this prefactor. And we just said that, okay, asymptotically it should behave like that exponential, but the exact solution, of course, is not that exponential. So we said that let's factor out that exponential. What remains we called another function, and we obtained the differential equation for that other function. It is this one. And then we look for a series solution of that other function. That's most of the time the trick we use. And it turned out that if you want a normalizable solution, then epsilon should take specific values. It cannot take all the values. So this is also the steps that we will be doing out when we are studying the hydrogen atom. Now let's look at this alternative problem. Well, that approach doesn't really work so great in this case. So in this problem we have the potential. Now what we are imagining here is just this bouncing ball. So the potential, if x is larger than 0, is just mgx, and if x is less than 0, it's infinite. So this will be a simple model of this bouncing ball. And so we will be looking for the solution of this equation. Plus, let's say, v of x psi is equal to e of psi. Now for psi of x, since we have infinite potential at the x less than 0 range, this should be 0 if x is less than 0. Otherwise, that equation cannot be satisfied. V is infinite, psi should be finite, psi should be 0 so that the product can be 0. And we can satisfy this equation. The left-hand side will be 0, the right-hand side will also be 0. And so for x, the problem is, what is the solution for x larger than 0? Now for x larger than 0, if you just write the differential equation, dx squared plus mgx psi, this should be e psi, where the boundary condition is psi for x is equal to 0 should be 0. This is the solution we are looking for. And psi of x should also go to 0 as x goes to infinity. So basically, these are the solutions we want. They start from 0. They might have a bump, but eventually, when x is in the classically forbidden region, it should decay exponentially and go to 0. Or it can have one bump and cross to 0 once and then go to 0, cross to 0 twice and then go in the classically forbidden region and exponentially go to 0. Those are the solutions we are looking for. Now, first we just determine what are the natural units of our problem. It's definitely not meters, seconds, etc. So to determine some quantity that has the unit of length, just again note that h bar squared over 2mx squared should have the same unit as mgx. Or x cubed should have the unit of h bar squared over 2m squared g. Well, 2, just drop it, it doesn't have any units. So x, we can define an x0. Well, let me also put the 2 there. H bar squared over 2m, m squared g to the power 1/3. I mean, whether you put the 2 there or not doesn't really make any difference. And I will define x to be x0 times u. So if you go back to our differential equation, so minus h bar squared over 2m d squared psi by x0 squared du squared plus mg x0 psi x0 u psi should be equal to e psi, or d squared psi by du squared minus 2m squared g x0 cubed over h bar squared. U psi should be equal to minus 2m e over h bar squared. H bar, and here I have the x0 squared. And this, if you just use our definition of x0, this is just 1. Let me call this, here I have a psi, let me call this coefficient epsilon. So d squared psi by du squared plus epsilon minus u psi is equal to 0. This is the equation that we are trying to solve. And the energy of my system is just h bar squared over 2m x0 squared epsilon. And keep in mind that epsilon will be eventually just a number. You see, the eigenvalue equation for epsilon doesn't have any free parameters. So for example, if you double the mass of your particle, the energy values will just go half. We already know how they will behave as a function of the mass, for example. Oh, sorry, x0 also contains the mass, sorry. Not half, but we know how it will behave. Well, you see, this whole thing I called epsilon. And if you just solve E from that equation, this is how E is related to epsilon. And epsilon is independent of the parameters of my problem. Epsilon will be independent of mass, it will be independent of h bar, it is independent of g. Because the equation, the eigenvalue equation that determines the possible values of epsilons do not contain any free parameters. It will be 1, 1.4, etc. It's unitless. Now let's see. Let me just make one more change of variable over there. Let me just call z is equal to epsilon minus u. So that my equation just becomes plus z psi is equal to 0. The second derivative with respect to u is the same as the second derivative with respect to z. So you see, there's not even an eigenvalue equation anymore. Everything is known. The solutions are also known. The solutions are called the area functions. Again, it's a second order differential equation, so it has two solutions. One of them will not be normalizable. Now, just like in the previous case, one of them goes to 0 exponentially, the other one diverges exponentially. So what we are interested in is the one that goes to 0 exponentially. So psi of z, let's say that is called ai of z. Now, if you plot this function, this is a nice function. So this is my z value. So for positive values of z, it just goes to 0 exponentially. And for negative values of z, it is just oscillating. It just looks like something like this. This is the solution. This is the area function. Well, that is kind of what we expect from our general solution. You see, in the classically allowed region, we want some oscillations. In the classically forbidden region, it should go to 0. Now then there is, of course, the question, well, this is just one solution. We have to find all the eigenvalues and eigenfunctions. There should be many of them, not just one. But you see, this is psi of z. So psi of u, this is ai, and keep in mind that z is just epsilon minus u. This is my psi of u. And I have a boundary condition. X is equal to 0 just means u is equal to 0. So it already satisfies this boundary condition. So psi of my boundary condition tells me that psi at u is equal to 0 should be equal to 0. Now let me just check one thing. I might be missing the signs. Yes, this is u minus z. So this is minus z. U minus epsilon. Okay. Psi of u is equal to 0 should be 0. So this tells me that I of minus epsilon should be equal to 0. So you say epsilon now has only can take all the possible discrete values. This is my minus epsilon 0. This is my minus epsilon 1. This is minus epsilon 2, minus epsilon 3, etc. So psi n of u is ai of u minus epsilon n. So these are my solutions. And although they are all written in terms of a single function ai, you see what we are actually doing. We are basically shifting this solution our solution for the linear potential will be, well, you see, we are just shifting them. Shift this such that the x is equal to 0 just correspond to this point. So this is our ground state solution. It is 0 below this point. The first excited state, well, shift the z is equal to 0 point to here. So our first excited state crosses the 0 once, and then again it goes exponentially. Z is equal to 2, the second excited state has this shape. It crosses, besides the z is equal to 0 point, it crosses the psi is equal to 0 twice, and then decays exponentially. These are my solutions, how they will look like. This is the third excited, fourth excited, fifth excited, etc. Although they are all written in terms of the same analytical function, they are different. Well, I think it's obvious that they are different, and they form a complete set because they are eigenvalues of a Hermitian operator. They have to be complete. Any function can be written in terms of these, etc. And the zeros of the solutions of these equations are tabulated, etc. You can just look them up. Well, the series solution for the Aries, I mean, it's not as nice as the harmonic oscillator. But fortunately, at least we know the solution of this differential equation. And in fact, this is one of the few examples which we can solve exactly. So now the next task. What if we have an arbitrarily complex potential? How can we at least approximately find the solutions, the eigenfunctions, the eigenvalues? Most of the time, the eigenvalues will be more important for us than the functions themselves. And that brings us to some approximation methods. Now, any questions on this linear potential? Well, okay, how do you know that there are such functions AI? Well, you go and talk with your friends in the mathematics department. They will tell you that this differential equation has some solution, has known solutions with known properties. So then you will say, those are my functions, my eigenfunctions. Or if you like using Mathematica or in other symbolic mathematical programs, you can just ask Mathematica for the solution. It will tell you what the solution is. You don't need to memorize these AIs, but of course, given some of their properties, you are expected to be able to make derivations from those properties. You see, let me just summarize what we will be doing in this WKB approximation. We will not be going into too much detail. Let's just assume we have a one-dimensional problem and we have some kind of a complicated potential, let's say. It can have whatever shape you like. Now, what we will try to do is, you see, in this range, most of the time, the function is just constant. It doesn't change much. So that will allow us to find an approximate solution in this region. Well, in this range, my function goes to 0 anyway. So I don't really need a very precise expression for my wave function. Well, it will not contribute to many things. And there is this range. Well, let me just move them a bit inside. And then there is also this range. Where my potential is almost linear. So what I will try to do is look for some approximate solutions in this region, some approximate solution in this region, using the fact that either my function is almost 0 or the potential doesn't change significantly within that range. And then I will just match the solutions in these two regions using the solution for a linear potential. And we have just seen that the solution for the linear potential are just area functions. Of course, since that is a finite range, within that finite range, I can have both of the solutions of my linear potential. We only had discussed the AI. Other solution is BI, but BI just diverges for large values of Z. But since here we are looking for a finite interval, within this interval it cannot diverge, so we have both the solutions AI and BI. And then just using these areas, we can match the solutions in different regions. So that will just give us an approximate solution of our wave function, which is constructed by kind of a patchwork. So we will just determine our solutions at different regions and match the solutions in different regions using some other our area functions. Now let's proceed. This is the equation that we would like to solve. Or let me just write it in a slightly different form. no, sorry. Let me write E minus Vx. Now, the reason why I'm writing that E minus Vx is if you just think classically, E minus Vx is the kinetic energy, that is P squared over 2m. And if you write P as h bar k, that is just h bar squared k squared over 2m. So that whole thing I can just call k of x squared. This is how I define k of x. This is the definition of k of x, so that my Schrödinger equation takes this form. If the potential is, for example, a constant, k of x is just a constant, and if E is larger than the value of my potential at that point, then we have the sines and cosines or the plane wave solutions. If E is less than V of x, that is in the classically forbidden region, then we have the exponentially decaying solutions. Now let me look for a solution of psi of x in this form. Now, we had already made such an approximation. We had seen that omega x is more or less the classical action. Well, if you take the derivative, this just becomes I over h bar omega prime times psi. The second derivative becomes I over h bar omega double prime psi plus I over h bar omega prime squared psi. So if you just put them back, put it in our differential equation, we get minus 1 over h bar squared omega prime squared psi plus I over h bar omega double prime psi plus k of x squared psi should be equal to 0. Or psi should be, if we cancel the psi, we are looking for a non-trivial solution. We see that minus 1 over h bar squared omega prime squared plus I over h bar omega double prime plus k of x squared should be equal to 0. Now here I didn't make any approximation yet. Now what I will do is I will just ignore the second term. If omega double prime over h bar is much, much less than k of x squared, well, I can just put, I see that omega prime will be equal to h bar squared kx squared under the square root. Now, what does this mean? We will discuss in a moment. So for the time being, let's just assume that omega double prime over h bar is much, much less than kx, so I can just ignore that term. If that condition is satisfied, so omega prime is plus or minus this one. Or omega of x will be plus or minus h bar integral of square root of k of x dx. Let's say x prime up to the upper limit being x. Or my psi, I have two solutions, is approximately e to the power plus or minus I integral up to x of kx square root of, let me just write kx prime, k of x prime dx prime. And I have two solutions. Now that is also kind of expected. You say this is kind of the solution, the problem I'm looking for, I'm trying to solve. So if you think in terms of classical, this is, WKB is sometimes also called the semi-classical approximation. What we have is, if you have this particle, it will be just moving back and forth. It will just move toward the left, hit the turning point, and then move towards the right, hit the turning point, and turn around, move to the left, and it will just bounce back and forth. So that's why we have these two solutions. Each one of them corresponds to a wave. One of them is a wave moving to the left, the other one is a wave moving to the right. So that's basically why we have this solution. Now, this is in the classically allowed region. In the classically forbidden region, you see k of x is imaginary. You see, if you look at the definition of k of x, the classically forbidden region is for x, is the region where x, v of x is larger than e. So if v of x is larger than e, then kx squared is a negative number. If kx squared is a negative number, it just means that kx is an imaginary number. So we usually define k of x to be I times kappa of x being the real number. So psi of x is e to the power minus kappa of x prime dx prime integrated up to x for x goes to infinity. It's on the, in this region, this is the x goes to infinity range, this is the x goes to minus infinity range. So that is why we have we have this exponentially decaying solution, and psi of x will be equal to e to the power plus kappa of integral of kappa of x prime for x goes to minus infinity. This is again the exponentially decaying solution as x goes to minus infinity. So we already have some approximate solutions in various regions.
Hocam şimdi bu Week8 yaklaşımında biz elimizde non-lineer bir potansiyel ortam var. Biz bunu lineer ortamlara bölüyoruz değil mi?
No. You see, we are, I have my potential. I'm basically dividing it into various regions. Some of the regions, we will see that it satisfies this condition. In those regions, omega double prime over h bar will be much smaller than kx squared. That will be some of the regions. Some other regions will not satisfy this condition, but we are hoping that those regions, we will see that especially, for example, close to these turning points, at the turning point, kx is 0. But if kx is 0, well, you cannot have this condition. Well, let's say take the absolute value. The left-hand side is larger than 0, kx squared, it goes to 0, so this condition cannot be satisfied at the turning points. So these solutions that we wrote over here cannot be valid even approximately at close to the turning points. But that's not a big deal, because close to the turning points, the potential is almost linear. And close to the turning points, we have the other solution, the areas. We already know the solutions. And the next hope, next assumption, is that the region where the area functions give us an approximate solution of our wave function overlaps with the regions in which these exponentials give us a reasonably accurate wave function. That's another assumption we will make. Because if there is such an overlapping region like these regions over here, these are what I call the overlapping regions. In these regions, I can use both the solutions for the linear potential, the areas, and at the same time, I can use the solutions for obtained by these written by in terms of these exponentials over here. that will allow me to match these functions. You see, basically what I will be doing is, let's say if this is my potential, let's say, and I'm looking for a solution with this energy, you see in this region it should be exponentially decaying. In this range, it should be both exponentially decaying and it should also match with the Aries. If that is the case, then this exponential decay I can approximate as the tail of the Airy functions. And once I make that match, I can continue with the Aries, and the Aries will just start oscillating over here. Now I will assume that in this region, I can approximate it both by Aries and also at the same time by this exponential. That exponential will be some oscillating function. So my solution will be, well, okay, so it will just go down. It will start oscillate. It will oscillate. It will reach a region where I can use both Aries and my exponential solution. So here I reach this point using my exponential solution, using my oscillatory solution, and in this region I match it to my Airy solution, but my Airy solution tells me that it should have this form. Now in this region, both my Airy solution and the exponential solution should be valid. So beyond that region, I can just continue with the exponential solution. So beyond that region, I can continue with the exponentially decaying solution. And so now I have an approximate solution of my wave function. There is a problem though. You see, I said that the Aries basically have two kind of Aries that solve my linear potential problem. Both the AI and BI, they solve my linear potential problem. But BI, it doesn't exponentially decay, it starts diverging. So I should make sure that when I start from here, from the exponentials, and continue with the Aries, when I reach the other side, I should still be in the region where it is decaying. I shouldn't have some Aries in the region of the other turning point. I shouldn't have a solution which starts increasing. It shouldn't exist. It should decay in the classical forbidden region. But that means that I should have some matching condition. Now, the semi-classical approximation is basically because of this omega is more or less our action.
Bir şey sorayım. Şu V double prime çarpı E of H sıfır eşitliyoruz ya.
We are ignoring that.
Prime'la sıfır eşit olması gerekmiyor.
Not necessarily. You see, what I want is kx should be much larger than omega double prime. That's what I want. It doesn't necessarily need to be zero. Or you can look at it the other way around. This matching condition. You see, my particle starts from here. If you just follow the wave function, it just goes to, classically speaking, it goes to the other turning point and comes back to the initial turning point. The wave function should be the same. Because, I mean, classically speaking, there's no problem. The particle should have the same momentum. The wave function should be the same in quantum mechanics. The system should repeat itself in a sense, just means the wave function should be the same. But as you are moving in this direction, the wave function acquires a phase. This integral. As you are moving the other way around, still continues acquiring the same phase. So when it comes back, the phase should be 1 or minus 1. So then we get this condition that h bar k of x dx around the closed loop. This should be equal to h bar times n plus 1/2. This is our quantization condition now. Now let me check the coefficients. Yes. Let me just make a correction. This is h, or 2 pi h bar. Or if you want, you can just cancel the h bars. It just turns out that k of x dx, this is the total phase that my particle acquires as it goes from one turning point to the other one and come back. This should be some multiple of 2 pi. Well, there is also this additional factor of 1/2. Now, you see, there are basically two ways you can look at it. Now, I have these regions. Okay, where basically I match my exponential solutions using the area functions. So you see, on the far left, I have my exponentially decaying solution. In the middle, I have exponentially oscillatory solution. On the far right, I have the exponentially decaying solution. And these three solutions in the region between these exponential solutions cannot be applied close to the turning points because this condition is not satisfied. So these are only valid, those exponential solutions are valid only in three separate regions. They are separated by the regions close to the turning points. Now, close to the turning points, since I cannot use these solutions, I have to do something else. So what I do in close to the turning points is I just approximate my potential with a linear potential. The potential is almost linear if that region is closed. And for a linear potential, I already know the solution in terms of the area functions. Now, the one approach is that, okay, I have the area function, but this is a finite region. It doesn't go to infinity. So I cannot really say that, okay, I only will take the AI, the function that goes to 0 at infinity, because my range doesn't contain the infinity anyway. So I have these two solutions, AI and BI. Now, BI is kind of problematic because it starts diverging. BI increases. I start from this point. I'm matching. I start from this region where I have this exponentially decaying solution, decaying as it goes to infinity. Then in this region, in this common region, I match it with the AIs and BIs. And then I have this oscillatory solution in this region. And then I reach the other turning point. Around the other turning point, I match the different regions by, again, AIs and BIs. Then in the far end, I should have the exponentially decaying solution. In general, I will not have the exponentially decaying solution because I will not be able to match this combination of AIs and BIs with an exponentially decaying solution, in general. I will only be able to match them with an exponentially decaying solution for specific values of the energy. And those values of energy are given by these conditions. This condition should be satisfied. Now, we are not doing it explicitly here. We will not be using it that much, but just to give you an idea of what the WKB is and how do we get this Sommerfeld quantization condition. Well, another way of looking at it is, you see, if you just consider these waves, we are basically moving from one turning point to the other one and back. If your particle just starts from one turning point, goes to the other one and comes back, it's at the same point it should have the same phase. The wave function should be the same. Well, I mean, the wave function has a single value at every point. If you just follow how the phase of your wave function changes as you start from the initial point, from one turning point, just sum the changes in your wave function until you go to the last point and then come back, you are basically at the same point. Your wave function should have the same value, including the same phase. But it always gained phase. You see, if you look at this, your solutions over here, as x is increasing in one direction, you get the one sign, so the phase is increasing. If you just move the other side, you'll get the minus sign, so again the phase is increasing. So the total increase in the phase need not be 0, but it should be a multiple of 2 pi. Well, the reflection causes this additional 1/2. So that's basically how you obtain this Sommerfeld quantization condition. So this kx dx is basically the amount of phase it gains as it just makes one round trip, in a sense, in a semi-classical sense. This is also another reason why we call it the semi-classical.
Yani wave funksiyonun aslında tamamıyla kompleks bir single root bir function olması lazım.
Yes, exactly.
1/2'de reflection'lar geliyor dediniz. O sekanlar mı bir şey geliyor? Ama onlar interfere etmez mi sonra kendisi?
That's why, if it interferes, you don't get a wave function. This is what, if this is satisfied, well, it interferes, of course, then you get this standing waves. You see, if you want standing waves, the wavelength should have some finite, some specific properties. The wavelength should be some integer. An integer multiple of wavelength should be equal to the total length. Kind of. This is, if you just repeat this procedure, assuming V is constant, this condition is nothing but the total length of, if you just apply this to a particle in a box, this is just a condition that the wavelength should be some multiple of the wavelength should be the total length of the box. This is exactly this condition. Of course, assuming that even if the potential is slightly changing, then the wavelength at different regions will be different. So you cannot really say a unique wavelength, but then the total, in a sense, that this multiple of wavelength will be just this integral. Kind of. Now let's go back to this condition over here. Omega double prime should be much, much less than k of x squared. Omega prime is h bar k of x. Okay, so omega double prime is h bar dk by dx. So omega double prime over h bar is much, much less than k squared condition. Basically means that dk by dx, hold on, am I missing some factors over here? Okay, no. dk by dx should be much, much less than k squared. So dk by dx times 1 over k should be much, much less than k. Now, if this was just an ordinary wave, k is nothing but 1 over lambda. So dk over x, dk by dx of 1 over k is lambda times d lambda over dx 1 over lambda squared with a minus sign. So this is minus d lambda by lambda. Now let me put the absolute values here. So d lambda by dx 1 over lambda should be less than k. Well, okay. Now you can just play with it around whichever way you like. Probably this will be much better, 1 over lambda. Now what is k? K was 1 over h bar square root of 2m e minus v of x. Now dk over dx, so that's basically how fast k is changing, but that is also a measure of how fast v is changing. So this number over here, 1 over k dk by dx, is basically how fast the v is changing, or the inverse distance over which v changes significantly. This should be much less than 1 over lambda. Lambda should be much larger than 1 over k dk by dx. So the wavelength of our state should be such that the potential doesn't change much over the wavelength, over a single wavelength. So it should be, the potential should be changing smoothly such that it doesn't change significantly over one wavelength. So this is basically what our condition, that omega double prime should be much less than k squared, tells us. So it should be smooth, meaning that, okay, if you just imagine over which distance it changes by, let's say, 50%, that distance should be much larger than the wavelength. So this is just a means of obtaining an approximate solution, whatever the wave function is, whatever the potential is. So, for example, for the hydrogen atom, it just worked quite well for quite a long time during the times of the foundation of quantum mechanics. Or for the harmonic oscillator, it also works quite fine. Here we are not really assuming too much. The only thing we are assuming is that the potential doesn't change much over one oscillation of our wave. So if you cannot do anything about your potential, if you cannot find an analytical solution, this is a way of finding the energy eigenvalues and approximate wave functions also. Although we didn't go into too much detail, this is the basic idea. Then eventually we will study some other methods, like if you have a harmonic oscillator, but there is a small, we have to quantify that small also with a small correction to the harmonic oscillator potential. We will also look at ways of obtaining the approximate eigenvalues and functions, which we will do in perturbation theory. But I mean, that is applicable only if the correction is small. This WKB is applicable whatever your potential is. Okay, so I will just close these topics over here unless you have some questions. You see, the main lesson over here in the WKB approximation is here is our quantization condition. If you need the wave functions, of course, then you have to work out the details over here. But the wave functions are also have these behaviors in various regions. So we know more or less what the energy eigenfunctions will look like. Any questions about this, about the previous things?
Hocam ben bir şey soracağım da. Saçma da olabilir. Şimdi chapter'ın başında şey diyordu. Zaman bir operatör değil, bir parametredir diyor.
Hı hı.
Şimdi elimizde bir şey var diyelim. Bir foton var. Ben bu fotonu işte ilerletiyorum. Bir tane de alet var elimde. Böyle bir ışığı uzayda değil de zamanda bir şey yapıyor. Modüle ediyor. Yani şöyle mesela bizim kullandığımız SLM'ler var değil mesela. SLM'ler ışığı uzayda modüle ediyorlar. Faz veriyorlar. Bu fazını benim de elimde işte şeyde değiştiriyor. Zamanda değiştiriyor. Yani frekansıyla falan oynayabiliyor. İşte ama bu alet işte uzay zamanı büküyor. Böyle bir uzay zamanı büküyor. Farklı bir şeye geçiyor diyelim ya da farklı bir yani farklı bir zamanda şey yapıyor. Biz burada zamanı şey olarak kullanabiliyoruz mu? Operatör olarak kullanabiliyor muyuz?
In this formulation, no. Time in this formulation is never an operator. In this formulation, position is an operator. But for example, if you do a relativistic formulation, because relativity tells us that time and position are not so independent quantities, they should have more or less an equal footing. In a relativistic formulation, also position becomes the parameter. There is no position operator in a relativistic formulation. So rather than being able to promote the time to an operator, we demote the position to a parameter so that they will be on equal footing. Now, in a different way of looking at it, how do you measure time? That was one thing we had been discussing. How do you measure time? Yeah, how do you measure it? You look at your watch, right? You look at your watch. But when you look at your watch, what you basically do is you just look at the position of something and relate that position to time. I don't know any measurement of time, direct measurement of time. So in that sense, it's not an operator. Again, that's a position measurement. You are measuring position. And from that measurement of position, you are inferring what time should be, how much time has passed. So you're not directly measuring time. You are measuring something else from which you determine time. Basically the same thing. You measure the vibrations. That's the vibrations of the light emitted by those atoms. But in a sense, the same thing holds for position measurement too, in a sense. So what do? You look at your watch, you look at different positions and see if the hand is at that position or not. Right? So in that sense, you are not even measuring position. You are looking at the position and looking at the number of particles at that position. You are measuring the number operator. That's what we do in relativistic formulation, in quantum mechanics. We cannot define a position operator, but we can define the number density operator, let's say, at a given position. So then you say that, okay, if the number density of my particle at that position is 1, the number of particles in that region is 1, then the position of my particle is at that point. That is what we are basically saying. We are measuring the size of the universe. Again, we are measuring length, not time. No, we do. Yes, we know the center. It's everywhere. Everywhere was the center. Just think of it like, I mean, the typical classical example is a expanding balloon. You see, if you have an expanding balloon, there is no point on the surface of the balloon from which it started expanding. It started expanding at every point. The same holds for the universe. The universe exploded at every point, and it's expanding at every point of the universe.
Bir nokta patladı, o nokta 2 nokta, 3 nokta, 5 nokta, 10 nokta falan öyle oldu.
Well, kind of. You cannot count the points, but kind of the idea. Okay, that point just became all of the universe. It doesn't correspond to a point in our universe. All of the universe was that point. You see, what you are imagining is that point was a point in our universe, and that point expanded. So, but what I'm saying is that that is wrong. That point was not a point in our universe. That point was the universe. Well, I mean, that's a good example. When the babies grow, I mean, they didn't grow from one single cell. All of the baby it grew from a single cell. There is no center cell. Just like the universe, there is no center point of the universe. All of the universe started from the same point. In a sense. There is no center of that sphere on the sphere, though. Okay. So see you next week, if we can still have a lecture on Monday. Well, I mean, there are rumors that Monday will be a vacation after the referendum. I mean, I don't think it will be due in the universities, might be in the high school. So anyway, if there will be lectures, see you on Monday, otherwise see you on Wednesday.